This question asks us to calculate cell potentials from half reactions, and they give us clues as to which half reactions we should consider in the problems. There is a bit of a formatting challenge here, but we'll address that as we go along. So in problem A, my red letters, which may differ from yours, include permanganate ion on the reactant side. So given that I have permanganate, I'm looking at any reaction that might have permanganate. Here's one. Here's one. And here's one. 3 possible reactions. On the product side, the manganese-containing product is manganese 2+ ion. So that eliminates this permanganate, as well as this one. So that leaves us just with one possibility. And the fact that permanganate's on the reactant side means that this is going to be our reduction reaction. The other reaction, or red letters, that I have are iodide ion on the left side and the iodine molecule on the right side. So I'm going to glance through table 17.1, looking for a reaction that contains both iodine molecule and iodide ion. Here's one. Notice that the iodide ion appears on the right side in the table of standard reduction potentials, but on the left side in the overall equation that they've started for us. That means that that reaction has been flipped around. It's the oxidation reaction. Let's do a little work down below involving redox balancing, just to make sure that we've got all the coefficients in the right place and so on and so forth. But we'll note the 2 reactions we're dealing with in this cell and their associated voltages. Okay, straight from the table. Permanganate plus 8 hydrogens plus 5 electrons yields manganese 2, 4 waters, with a voltage of 1.51 volts. For the oxidation side, we've got 2 iodide ions becoming iodine and 2 electrons within a voltage of, after flipping it, negative 0.54 volts. The electrons have to cross out. So I'm looking in the reduction reaction, I see 5. In the ox reaction, I see 2. Lowest common multiple between 5 and 2 would be 10. So let's double the permanganate reaction and quintuple the iodide. Rewriting everything. Note, unlike Hess's law in thermodynamics, where if you double the coefficients in a reaction, you would also double the value for delta H, you do not do that here. That's because a voltage is a ratio. It's the number of joules of energy per coulomb of charge. So it is already a ratio. Increasing the number of molecules present would increase the number of joules of energy, but it would not affect the ratio of joules per coulombs. So keep that voltage at 1.51. It's very tempting to double it, but don't. And multiply by 5 all the coefficients in the oxidation reaction. Again, keep the voltage the same. Let's add those 2 half reactions together, making sure that the electrons cross out. What do we have at the end? And let's include states of matter, because WebAssign's going to ask us to list those. If it's an ion, it's always going to be aqueous. So we've got permanganate, we've got 16 hydrogens, we've got 10 iodides. And then on the right side of the equation, we've got 5 iodine molecules, 2 manganese 2 ions, and 8 waters. Now water's a liquid, so put, for state of matter, put a liquid. And then to get the overall voltage, I'm going to add together a 1.51 plus a negative 0.54. That's a positive 0.97. Okay, now for the formatting bit. If you look up above, the first box is the box that they want you to put the coefficient in. Then either WebAssign gives you the formula followed by the state of matter in parentheses, or they'll give you a box in which to write it. So on the left side of the equation, we have a coefficient 2 in front of permanganate. Let's write that down in the box in front of permanganate. And they're telling us it's aqueous, and we agree that it's aqueous. Okay, fine, that's already written. Next ion they want you to write is the iodide ion. Our coefficient is 10. Okay, let's write it 10. And they included the state of matter there. Good, we're done with that one. What was the other ion on the reactant side? The 16 hydrogens. Okay, so first box, the coefficient 16. Next box, H plus the formula for hydrogen ion. And then the third box, and you could maybe see the parentheses they're showing us there, they want you to type in AQ. It's an annoying little formatting issue. On the right side of the equation, we have, first they're calling for the coefficient in front of iodine molecule. Okay, we've got that, it's 5. Then they're calling for the coefficient in front of permanganate, or I'm sorry, manganese 2. It's a 2, so let's write that. And they've written the formula and the state of matter. And then there's one other species that we haven't written out yet, and that would be water. There's 8 water molecules, and the state of matter for water under normal conditions is liquid. So put an L in the box. Last point, or last piece here, they asked for the voltage. We'll put down 0.97. And as with any galvanic cell, you've got to have a positive cell potential. They're indicating a galvanic cell here because we have a positive voltage. So that is SPONT. In much the same way in thermodynamics that a negative delta G indicates spontaneity, in electrochemistry, a positive cell potential indicates spontaneity. Okay, problem B. We've got, again, look at this, permanganate appears again for us, along with manganese 2 ion. As we analyzed above, that's going to be the same half reaction, the one that has permanganate and 8 hydrogens and 5 electrons becoming manganese 2 and some water with a voltage of 1.51. Now, what about the other half reaction? Oops. Okay, the other half reaction. What are our clues as to what that could be? Well, they tell us we've got chloride ion and chlorine molecule. Is there any half reaction in this table that involves both chloride ion and chlorine molecule in the same half reaction? Here it is. It's written, of course, reduction style in the table of standard reduction potentials, but that's going to be our oxidation reaction. So we're going to have it flipped around. The voltage as listed in the reduction table is a positive 1.36, but when we write it as an oxidation reaction, it'll be a negative 1.36. Let's write down what we know. We've got the same reduction reaction as before. And our oxidation reaction is 2 chloride ions becoming chlorine molecule with 2 electrons left over. Voltages. A positive 1.51 volts for the permanganate reaction, and after flipping it around, it's a negative 1.36 volts for the chlorine reaction. Do the number of electrons match? No. We've got to multiply by coefficients in order to get them to match, otherwise it won't work. So lowest common multiple between 2 and 5, 10. So double all the coefficients in the permanganate reaction. Multiply by 5 all of the coefficients in the chloride reaction. Let's write down those results. The voltage does not change upon multiplying. Now let's add the two half reactions together, and let's look for electrons to cross out, and they do. Wonderful. We'll write the total overall equation, and we'll include states of matter because Webassign wants us to. The chlorine that they produce is a gaseous chlorine. Chlorine is it's a halogen, but the chlorine molecule exists under normal conditions in gaseous form. Okay, so we've got states of matter. We've got good coefficients. Let's add these together. Positive 1.51 minus 1.36. We get 0.15 volts. Okay, and then let's enter all of the relevant info. The first box, they want the coefficient in front of permanganate. It's a 2. Next box, they want the coefficient in front of chloride ion. We found it to be 10. And then they give us 3 empty boxes. The 3 empty boxes would be whatever else hasn't been written down yet. So the 16 hydrogen ions in aqueous, that are aqueous in state of matter. So write 16 and then H plus and then AQ within the parentheses. Next box, on the other side of the reaction arrow, they want the coefficient in front of chlorine molecule, which is a 5. Then the coefficient in front of manganese 2 ion, which is a 2. And then the third species, which they don't give you any hints about, but it's going to be what we have left over, 8 water molecules. State of matter for water is liquid. And then last piece, we've identified the voltage as a positive 0.15. As long as it's a positive cell potential, then it's a spontaneous reaction.